Welcome to Level 3. Today we're diving into potential in plates, focusing on how uniform fields and scalars work in one dimension. Let's start on the left with problem 9. We have an 8.8-volt battery connected to two plates separated by 4.4 millimeters. To find the electric field magnitude, remember that in a uniform field, the E field is simply the voltage divided by the distance. Quick tip, make sure to convert those millimeters into meters before you calculate, or your final answer will be off by a factor of 1,000. Now shifting over to problem 8 on the right, we're looking for the total electric potential at x equals 0.5 meters. We've got a positive charge at the origin and a negative charge 1 meter out. Because potential is a scalar, you don't need to worry about vectors or angles. Just calculate the potential from each charge independently and add them together. Keep a close eye on your signs though. That negative charge is going to reduce the total potential at the center point. Go ahead and pause the video now to try these on your own before we walk through the solutions. Alright, let's see how you did. For solution 9, the biggest hurdle is that trap alert, converting millimeters to meters. Once you have 0.0044 meters, you just plug it into our formula, E equals V over D. Dividing 8.8 by that distance gives us a clean electric field of 2,000 volts per meter. Moving to solution 8, remember the core concept. This is a scalar sum. We use the formula V equals KQ over R for both charges. Since both charges are 0.5 meters away from our target point, we can factor out the constants. Notice how we kept the negative sign for the second charge? That's crucial. When you sum them up, the potentials partially cancel out, leaving us with a final result of approximately negative 46,748 volts. It's a large number, but remember, since potential isn't a vector, we don't care about direction, just the total energy landscape at that spot.